Hi everyone, welcome back to Code Cogs. You go to channel for data structure and algorithm. I'm Shamitu Devranga. In this video, we are going to break down a very important topic in computer science, time complexity. If you are preparing for code interview, building scalable software, or just want to write smarter code, understanding time complexity is a must. So let's get started. What is time complexity? So what exactly is time complexity? Time complexity measures how long an algorithm takes to run based on the size of its input, which we often represent as n. For example, if you are searching through an array of 10 elements, it might take 10 steps. But what if it's 10,000 or 1 million? That's where time complexity matters. It gives us a way to compare different algorithms regardless of the hardware or programming language, and helps us predict performance as input grows. So it's like the speed rating for your code. Why is time complexity important? Now let's understand why this concept is so important. When we build software, especially at scale, time complexity affects everything: speed, performance, user experience, and cost. It helps in selecting the most efficient algorithm. It's essential in competitive programming where time limits are tight, and its favorite topic in technical interviews. Trust me, almost very good company will test your understanding of time complexity. So if you are aiming to become a strong developer, you simply can't ignore this topic. Big O notation. Let's move to the most common way we describe time complexity, Big O notation. Big O tells us the upper bound or the worst case time an algorithm can take. For example, let's say we have this loop. For int I equals 0, I smaller than n, I plus plus. This loop runs n time. So we say the time complexity is O of n. We read it as big O of n. Why do we care about the fourth case? Because it prepares us for the slowest possible performance, the one that could break our application under pressure. Some common Big O notation now: O of 1 constant time, O of n linear time, O of n squared quadratic time, O of log n logarithmic time, O of n log n, or O of 2 to the power n, and more. Each of these tells us how the time grows as input grows. Common time complexities. O of 1 constant time. This is the fastest possible time complexity. It means the algorithm always takes the same amount of time no matter how large the input is. Even if the array has one item or 1 million items, we are just accessing the first element super fast, super efficient. Next, of log n, logarithmic time. This occurs in algorithms that divide the input in half each time. Example, binary search. If you have 1000 items, binary search will find the result in about 10 steps, because 2 to the power 10 equals 1000. It's fast and powerful, but only works on sorted data. Next, O of n, linear time. This means the algorithm processes each element once. If you have 10 items, it takes 10 steps. If you have 1 million, it takes 1 million steps. It's predictable but not always efficient. Next, n log n. You will find this in efficient sorting algorithms like merge sort and quick sort. It combines both linear and logarithmic growth, making it one of the best choice for sorting large datasets. Example, quick sort. It's faster than bubble and insertion sort, especially with large inputs. Next, of n squared, quadratic time. Now we are getting into danger zone. This usually happens with nested loops, where for each element we perform a full screen again. If n equals 1000, that's 1 million operations. You can see how quickly it grows. used in brute force algorithm or naive comparison like checking all pairs in a list. Next, O of 2 to the power n. Exponential time and O of n factorial time. These are extremely inefficient. They grow so fast that they are unusable for large inputs. Examples are solving the traveling system problems or generating all subset of a set. These are often seen in backtracking or a recursive problem like the Fibonacci sequence. As you can see, small differences in complexity can use huge differences in performance, especially for large inputs. Let's take a moment to visually understand how different time complexities behave as the number of input element increases. This chart shows operation of the y-axis and input size element. On the x-axis, each curve represents a different big or time complexity. Red zone, horrible performance. O of n factorial of 2 to the power n, O of n squared. This algorithm grows very fast. As the input increase even a little, the number of operations skyrockets. Example, solving a traveling salesman problem or deeply nested loop. Avoid these unless you are working with very small inputs. Orange zone, back to pair. Of n log n. Found in efficient sorting algorithm like merge sort and quick sort. Much better than quadratic time, but is still noticeable for very large inputs. Yellow zone, fair, often linear time, scales directly with input size. It's acceptable and often seen in loop that process each element once. Next, green zone, good to excellent, of log n and of 1. These are the best performer. Of log n is seen in binary search. O1 means constant time, like axis and array element. These are your idea targets when optimizing performance. As the input grows, the difference between these time complexities become massive. Always aim to keep your algorithm in the green or yellow zone and avoid falling into the red. Code examples. Now let's understand this with real code. Return array 0. No matter how large the array is, it's returned the first element in constant time. Often, for int I equal 0, I smaller than n I plus plus, sum equal sum plus array I. We go through the array once, so it's linear. Of n squared. For loop int I equals 0, I smaller than n I plus plus. For loop int j equals 0, j smaller than n j plus plus. Print I and j. This is a nested loop and performance drop fast. For example, if n equals 1000, you are doing a million operations. These are just a few examples, but the principles stay the same. Fewer operations equal faster code. Best, worst and average case. Next, let's talk about 3 common scenarios. Best case. The algorithm finishes quickly. For example, if the first element in a search is the one we want. Worst case. The algorithm takes the longest time. Maybe the desired element is the last one. Average case. The expect time across various inputs. Big O usually focus on the worst case, but it's also good to be aware of the others, especially the optimization performance in the real world apps. Tips for optimization. Now here are few tips to help you reduce time complexity in your programs. Avoid unnecessary nested loop. Use efficient data structure. For example, use a hash map instead of scanning a list. Choose faster algorithms like merge sort or quick sort. over slower ones like bubble sort. Remember, sometimes changing just one line of code can improve performance 10x or more. To sum it's all up, time complexity is essential for writing efficient and scalable code. Big O notation helps us evaluate algorithm performance and make the right choice. Always try to reduce complexity and optimize your code. That's all for today's video on time complexity.